Hey everybody, I hope you're enjoying Snowpocalypse Round 2. Wanted to start off the review, or the answers to the capacitor problems with a quick review of capacitors, since we went over it pretty quickly in class the other day. But, the main equations are just that capacitance equals charge divided by voltage. From that equation you can derive that charge equals capacitance times voltage. And again, potential energy equals 1/2 QV. And again, if you substitute in your capacitance equations, you can derive the equation U equals 1/2 times capacitance voltage squared, and also potential energy equals 1/2 charge squared over the capacitance. If you have capacitors in series, they act much like resistors in parallel. So to calculate your equivalent capacitance, you've got 1 over the equivalent capacitance equals 1 over C1 plus 1 over C2 plus 1 over C3, etc., as many capacitors as you have in series. When we're talking about the voltage total, remember from Kirchhoff's law, if you make a complete loop around a circuit, get back to the same point, that voltage is going to be equal. So those capacitors have to use up all the voltage that's available. So for that would mean that voltage of capacitor 1 plus voltage of capacitor 2 plus the voltage of capacitor 3, on and on until voltage N is going to add up to the total voltage available from the source. And then the charge on the plates of the capacitor, the total charge is just going to equal the charge on any one of the capacitors that are in series. Continue on with parallel capacitors. Parallel capacitors, as we talked about, act much like resistors in series. So we've got our equivalent resistance just equals capacitance 1 plus capacitance 2 plus capacitance 3, etc. Voltage total, again, if things are in parallel, they have to have the same voltage across them. So V1 equals V2 equals the total voltage. And then the charge on the capacitors. The total charge is just going to equal the charge on the first capacitor plus the charge on the second plus the charge on the third, as many capacitors as are in parallel. And again, remember that once the plates on a capacitor are charged, there's no current through the circuit. So those capacitors just act like an open circuit. And the voltage drop across the capacitor would just be the charge divided by the capacitance, or said another way, the potential difference of a capacitor once the plates are fully charged equals Q over C. And now our capacitor homework problems. I'll try to go through these pretty quickly. I've written out the solutions, so if you just want to review your work, you can hit pause, not listen to me, and make sure you have the answers correct. But we have our 3 capacitors in series, a 6 microfarad, 4 microfarad, and 2 microfarad capacitor, all hooked up to a 12-volt battery in series. We're trying to find the equivalent resistance. We said capacitors in series, when we're finding the equivalent, it's like resistors in parallel. So we have our equation 1 over equivalent resistance equals those 1 over all of those capacitances. That gives you the equivalent capacitance of 1.1 microfarad. Trying to find the total energy stored by the circuit, that's just going to be our equation U, potential energy, equals 1/2 times capacitance equivalent times voltage squared. So we have our 1/2 times 1.1 times 10 to the minus 6th farad capacitance times 12 volts squared. That equals 7.9 times 10 to the minus 5th joules. And now for part C, we're going to find the voltage drop across each capacitor. You'll remember that for capacitors in series, the charge total just equals charge 1 equals charge 2 equals charge 3. So let's find our charge total. We'll use our Q total equation equals equivalent resistance times voltage. So our equivalent resistance, 1.1 times 10 to the minus 6th farads times 12 volts equals 1.3 times 10 to the minus 5th coulombs. And so again, from our series capacitance, the charge on A is equal to the charge on B is equal to the charge on C, which equals 1.3 times 10 to the minus 5th coulombs. So our voltage drop across A just equals Q over the capacitance of A, equals 2.2 volts. For VB, same Q divided by the capacitance of B, 3.3 volts. And for our voltage drop across C, same Q divided by capacitance of C, 6.6 volts. And now for part D, for problem 1, we're going to find the energy stored by each capacitor. We'll use the voltage drop across each capacitor that we determined in part C to calculate the energy stored by each capacitor here in part D. So for the potential energy stored in capacitor A, it's going to be 1/2 capacitance A times voltage A squared, 0.5 times 6 e to the minus 6 times 2.2 squared equals 1.5 times 10 to the minus 5th joules. And for capacitor B, the potential in B is going to be 2.2 times 10 to the minus 5th joules. And lastly, the potential in C would be 4.4 times 10 to the minus 5th joules. Next, for problem 2, we have 3 capacitors hooked up in series that store a total energy of 2 times 10 to the minus 5th joules. And what is the voltage of the battery that they are hooked up to? So our 3 capacitors were a 5 microfarad, a 2 microfarad, and a 5 microfarad. We can determine the equivalent resistance, again from a series capacitor, or capacitors in series is that 1/over equation. So 1 over the equivalent capacitance is 9/10, and that gives us an equivalent capacitance of 1.1 microfarads. If we're going to find the voltage of the battery they're hooked up to, we can use our potential energy equation. U equals 1/2 C equivalent voltage squared. We'll solve that for V. Square root of 2 potential divided by the equivalent resistance, and that just gives us square root of 36, which is 6 volts. Now for problem 3, we've got our 3 capacitors again, but this time they're hooked up in parallel. So we have a 12-volt source, 6 microfarad capacitor, a 4 microfarad capacitor, and a 2 microfarad capacitor. And so we know that if these capacitors are in parallel, they're all going to have the same voltage. So to calculate our equivalent resistance, our equivalent capacitance of this circuit, we said that capacitors in parallel act like resistors in series, so we can just add those capacitors together. Equivalent capacitance is going to be 12 microfarads in this case. For B, the total energy stored by that circuit, potential energy is just 1/2 equivalent capacitance times the potential difference squared. So 1/2 times 12 times 10 to the minus 6th times 12 squared is 8.64 times 10 to the minus 4th joules. Next, we're going to find the charge on each capacitor. So to find that charge, we said that capacitance equals charge divided by voltage. Therefore, voltage is charge, therefore charge is capacitance times the voltage. So for Q1, we said again, capacitors are in parallel, so they have the same voltage. Q1 is C1 V1. V1 is just the voltage of our source, 12. 6 times 10 to the minus 6 times 12 equals 7.2 times 10 to the minus 5th coulombs. For Q2, just again, capacitance 2 times our voltage, 4 times 10 to the minus 6 times 12 equals 4.8 times 10 to the minus 5th. Lastly, for Q3, 2.4 times 10 to the minus 5th coulombs of charge. And now we're going to find the energy stored by each of these capacitors. So to find the energy stored by each individual capacitor, we're going to use our potential energy equation. So the potential in capacitor 1 is just 1/2 times capacitance 1 times the voltage squared. So 1/2 times 6 times 10 to the minus 6th times 12 squared equals 4.32 times 10 to the minus 4th joules. And then for capacitor 2, we've got 1/2 times 4 times 10 to the minus 6th times 12 squared equals 2.88 times 10 to the minus 4th. And then lastly here, for the potential of capacitor 3, 1.44 times 10 to the minus fourth joules. All right, for problem 4, we have 3 capacitors that are hooked up in parallel, and there is a total energy of the circuit as 8.64 times 10 to the minus fourth joules. And we said these capacitors are hooked up in parallel, so we can add their capacitances to find the equivalent capacitance. 5 microfarad plus 2 microfarad plus 5 microfarad equals a 12 microfarad equivalent capacitance. We have our potential energy equation is 1/2 times C equivalent V squared. Again, we're solving for V. V equals the square root of 2 times potential divided by the equivalent capacitance. So 2 times 8.64 times 10 to the minus fourth divided by 12 times 10 to the minus sixth equals 12 volts in this case. All right, lastly, we're going to work on our circuit with capacitors in parallel and in series.